Good afternoon. My name is Arvind Srinivasan. I'm here with my colleagues Anju and Matt. And Ashwin, the other person who did this work, could not make it to the conference. So we're going to be talking about analysis of network patterns for collective communications. So before we get into a little bit, I just want to give a background as to what led us into this work. And the main motivation towards this was to understand the performance bottlenecks that exist with collective communications and the challenge that exists as we scale this network. Now, I want to refer to the work that was done by our colleagues at Meta, and this was a paper that was published earlier this year. And the whole analysis was, okay, let's look at all the components of collectives and do a breakdown as to where the bottlenecks exist. So one thing that is certainly clear out of this particular work was the communication was a big bottleneck. And what we see is roughly 40% of the time is taken in the communication part of it. Now as we kind of scale the network, put more GPUs, or we see that the communication bottleneck increases even more. Also, within the communication itself, all-to-all and all reduces is something that really takes a lot more time. Okay, so now all-to-all typically is an operation that cannot be parallelized, or you have to do it you cannot overlap. And the time that you take in all-to-all really affects the overall training latency. So that was our clue saying, okay, let's just go analyze exactly what happens in all-to-all and kind of break it down exactly to see where the bottlenecks lies. Now, from here, I just want to give a little briefer on what an all-to-all looks like from a traffic pattern standpoint. Now, all-to-all is a case where every rank sends data to every other rank. A rank here is an equivalent to a process. So in this cartoon, what we are trying to show is, okay, I have 4 ranks. Rank 0 sends data to rank 1, 2, 3. 1 sends data to 0, 2, 3. And it's all nicely uniformly sent data. Everybody sending equal amount of data. It's a very simple example. Everybody sends 12 messages out. Every rank receives 12 messages, total amount of data. Now, in reality, so this looks very simplistic way, but in reality, what happens is slightly different. And that's what we want to go one click down, exactly what happens and where the scaling happens. Now, I want to point out to one other thing. So as we start analyzing this thing, we looked at exactly what happens in a particular node or how the communication libraries interact with the NIC. Now, this is a very simplistic state machine that we drew. Every node has an orchestrator who sends the data from one rank, who schedules the data to go from one rank to the other rank. So in this example, source rank wants to send the data to the destination rank. So the data is sitting in the accelerator's memory. It gets handed off to the network space. Okay, it goes in the data. Buffers are moved, pointers are moved, whatever, something happens there. Now, that involves some kind of wait states. It may not happen right away. There's some kind of a handshake that happens. Then, once that happens, that is step number 1 and 2. And afterwards, there are some exchanges that happens between the two nodes where some addresses may be exchanged. Kind of context is set between as to where this data is going to go. That's step number 2. Step number 3, sorry. The data starts off, now at that point, the NIC is given the data to hand off. The NIC sends the data on the Rocky network, RDMA network. Data moves to the destination side. The same thing happens on the other side. Data reaches the network space, gets handed off to the accelerator space. Potentially, there's some wait state involved, and so on and so forth. Now, data transfer phase is the big phase here, because that depends on how much amount of data needs to be moved. But one thing to note here is there are many steps that are involved to initiate a data transfer. And what we are showing at the top chart is, in some sense, the relative time for what each and every phase takes. And what we also notice now in this case, not every node runs equally. The phases that are being shown here are relative times, but they all vary between different node to node. Now, if we take this and map it to the diagram that we showed earlier, where everybody is moving data uniformly, now let's see what happens on the network. At this point, I want to hand off to Anju to walk us through the observations.
As Arvind discussed earlier, we saw that all-to-all communication is a critical bottleneck in our network, and hence we observe significant data transfer wait times. Now, to better understand the root cause of this performance degradation, we have an experimental setup here, as shown on the right-hand side, consisting of Xeon EX, which is an OCP hardware, connected to network fabric. The setup consists of 200 gig NIC endpoints and 4 AI nodes. Now, within each AI node, we have 8 accelerators. Hence, in total, in the setup, we have 32 accelerators, which has been named from accelerator 0 through 31 throughout the presentation. Now, 8 of them within an AI node, they use intra-node communication, and the remaining 24 of them, they use the RDMA network for data transfer. Now, looking at the network traffic pattern here, from the perspective of a single receiver accelerator, there are 24 sender accelerators sending packets over the RDMA network. Thus, we have a 24:1 communication pattern. Now, to gain deeper insights into this network pattern, we would need to perform a finer granular timescale analysis. Hence, we performed a packet capture and mirroring of the network traffic from the fabric to a single accelerator, which is indicated in the dotted line here. So all the packets from fabric to that accelerator is being captured to a collector host, and post-processing of the data was done. All the charts and analysis that you will be seeing in this presentation is based on the packets to this specific destination. Now, in an ideal scenario of all-to-all communication pattern, since every accelerator sends and receives the same amount of data to every other accelerator in the network, it should not oversubscribe the receiving accelerator. However, as you'll see in our coming slides, this is not always the case. Now, moving on to the next slide, where we have the observations. Here it's a view of ideal scenario versus what's actually happening in the network. So the following chart here, it indicates a time series representation of the packet sending rates, but from a sender point of view. X-axis represents the time in microseconds, while the y-axis represents the packet sending rate. In an ideal scenario, as you can see on the left-hand side, we would expect to see a uniform network traffic pattern where each of the sender is transmitting at 1/24 of the total bandwidth in a 200 gig network. However, as you can see on the figure on the right-hand side, in our experimental results, we observe spikes or bursts in the packet sending rates for an individual flow. Now, this is the case with just one flow. In a multi-node network, we have multiple flows from different senders. So in this specific pattern, in our setup for the all-to-all communication, there are 23 other flows being sent from the sender to 23 other destinations. Now, expanding this, let's take a look at in our next slides how this pattern would look like with multiple senders. Also shifting our focus from a sender point of view to a receiver point of view in our next slide. Now, the chart represented here, it shows the view from a receiver accelerator that is receiving packets from multiple senders. X-axis is again the time in microseconds, while y-axis is the receive rates. The different colors here, they indicate the multiple flows from different senders. Now, expanding on the ideal case scenario that we have seen in the previous slide, which is for just one single sender, now to multiple senders here, we would still expect to see a uniform traffic pattern, but since we have more number of senders, all of this should add up to 200 gig in a 200 gig network. However, as you have seen on the figure on the right-hand side, we observe large bursts or spikes in the received rates. This is due to the stacking up or lining up of flows from different senders, thus exceeding the threshold. Now, another interesting observation here is, if you recall the slide from, or the chart from our previous slide, the bursts were spaced apart, or maybe within a few microseconds apart. Now, when all of these bursts arrive at the receiver side, they can stack up at different times. To give an example here, the burst on the right-hand side, the larger one, the different color again indicates the flows from different centers. It's quite different from the one before. The main takeaway here is we have different flows coming from different centers at the receiver at different times, which makes the overall traffic pattern more unpredictable. And in the intensity of the burst varies as well. Now, this is the case with 24 accelerator. As we scale up the number of senders, the likelihood of this burst lining up and exceeding the line rate increases. There are also instances where we observe no burst at all, which can lead to idle time at the receiver. This you can see how all of these different network patterns can lead to degradation in the end-to-end performance. Now that we have seen the network traffic characteristics, let's explore how we can measure this burst and the implications on network design. I'll hand it over to Matt to discuss this.
Thank you. So Anju gave us an overview of what ideal all-to-all might look like from a network flow point of view, both from the sender and the receiver, and our actual observations in this test bed, which is representative of our actual network. What I wanted to go into is a level deeper and how this actually impacts things. It's like, so we see spiky patterns, so what, right? So all-to-all, as Arvind and Anju went into, is both an outcast and incast traffic pattern or workload, in that everyone is mostly sending to everyone at the same time, and naively you would think, well, okay, that creates an incast, but because you're sending to everyone, you get that 1/24 factor. All the rates should even out. It should, textbook, or if you run a simulation or something, look perfect, and that's not what we actually see. This is because our senders are not ideal. You saw a view of that on Anju's slide. So the net effect is we actually do get incast, and when the incast is sustained for a significant period of time, that leads to buffering. So to better quantify that and take a deeper look at it, what we did is we modeled the queuing behavior of the switch. So if you look at this chart, you see a red line. The red line is we modeled traffic going into the switch from whatever ports that is destined to a specific egress. And recall, the egress here is 200 gig. So anytime ingress is greater than 200 gig, we're going to see buffering. So we did that, and it's almost like a simulation. It's like a model on top of the actual packet capture to get a view of what's happening. So what you see here is a zoomed in view of a smaller portion of it. If we look at a larger view, it's much noisier and hard to look at it. So this is just a representative example. So here there's 4 bursts that are relatively close to each other. The first 3 are of similar size, the last one is larger. And what you see is when the bursts are very close to each other, the buffer goes up, and then time has to drain. When they're further apart, the buffer has time to fully drain. And like I said, this is a representative view. If you zoom out and look at the whole thing, there's times where the buffer will continue to accumulate. I mean, here we show at most 200 kilobyte of buffer, but it actually grows larger than that. All right, so the switch is buffering. That's what switches do. Switches buffer. People have been doing this for a while. Why is this a problem? It's because this is just a view of one port. Like when we build an actual system, we don't have 24-to-1 and that's it. Like we talked about, there's actually many of these incasts all happening simultaneously at a specific network element or in a rack. So take, for example, where you might have 16 NICs or 16 ports in a rack. Any buffering you see here due to one port, there's a probability of it also happening on the other ports. And we do see that. So the buffer is shared. I mean, it's a finite amount in the ASIC. So things are fine until you hit those cases where you start to consume a large portion of the shared buffer. Then you get ECN marking, you get PFC. That leads to end-to-end performance problems. So how do we solve this? I mean, this is a hard problem. So in the short term, you can use this as analysis and say, okay, this is how much buffer I need. If I don't want my network fabric to be a performance bottleneck, I can do this analysis, add it all up, and say, this is how much buffer I need if I don't want performance degradation. Unfortunately, we're not sure if that's going to scale. The network speeds are growing exponentially. Switch buffer might actually be decreasing relative to things. I mean, the SRAM isn't getting any smaller as processes shrink. So let's talk a little bit more about these bursts. There's been a lot of analysis on microbursts, on typical front-end, TCP type networks, and research into that. What's key about these that's different is they're generated by the RDMA hardware, by the NIC itself. On front-end networks, people talk about millisecond microbursts. Here we're talking about microsecond quantity microbursts. This makes them a lot harder to analyze. Like, you can't do rate sampling on millisecond boundaries to see these things. You need to be much finer grained. Currently, we're using hardware packet capture to see these. We're looking for more scalable solutions, both internally and from our partners. So anyone has some great ideas to collect this at scale, come talk to us. Here's 3 representative bursts. Like I said, it's very diverse if we look at everything. They're on the order of 250 to 300 gigabits per second, sorry, with widths on the order of 25 microseconds. And as I mentioned before, enough bursts on enough ports fill up the shared buffer, cause performance problems, and as Arvind mentioned at the beginning, up to 40% of the time in the training latency can be affected by the network, and it's something that we want to keep an eye on. And this is very challenging to address in the network fabric. The network's going to get faster and faster. The buffer's probably not going to get that much larger. We need to do something about this. So this is very difficult, and it can't be solved by the network fabric itself. Our opinion is co-design is a way to go about this. If the NIC, the network fabric, the collective communication library, they're all co-designed, being cognizant of that, and that's what's important. Like really, the takeaway from this is be aware of this. There's a qualitative be aware of it, but maybe there's some quantitative. Maybe we can work together to come up with methodologies to analyze this. When people have different options, how do we quantify which is better and which is worse for the cases of buffering and cast? Most of this analysis was around all-to-all on a specific model from an earlier meta paper. There's many different models, many different collectives. This is just one example. So how do you generalize this? Some work we've been doing with ML Commons and a few other companies is this Chakra project, which is execution traces of AI workloads. So those traces have useful information about the collectives involved, relative time. That can be used to sort of home in and quantify, like that 40% on the first slide, that can actually be quantified for other models. And with that, it's just, let's collaborate on this. This is going to be a hard problem to solve. We don't want to go at it alone, and we're looking for your help. Thank you.
Can we use an AI to solve this problem?
AI to solve AI. Maybe. That's all I'm going to say.
Quick question. So when you guys were testing all-to-all, were there like 24 RDMA streams going out from the NIC? Was that the case for your cases?
Yeah, so this is a standard all-to-all where, when you have this particular configuration with 4 nodes, with internode configuration, everyone is going to be sending 24 messages out and receiving 24 messages in.
Right. So the 24 RDMA sessions.
Yes.
I mean, we did similar experiments. What we noticed was the RDMA NIC was supposed to interleave all of the 24 streams equally, but it wasn't. They were bursts.
Yes.
Towards, I don't know if you guys were able to figure out on the RDMA NIC if there were any settings you could tune to actually reduce that and do an ideal interleaving of all of the flows rather than.
Yes, RDMA NICs have a lot of knobs. Unfortunately, most of these knobs aren't like standard. They're very vendor specific. So yes, we have experimented with knobs. I think some things might be able to be solved in the RDMA NIC, but I think the other elephant in the room is the collective communications library. In Arvind's slide, he talked a lot about, if you remember those relative times, the actual data transfer part was short. So that tells you, okay, that's the most I could probably affect by NIC knobs. How do I work on the rest of the problem?
Thanks.
Thank you very much.
Thank you.